So we just talked through and thought about what the sort of connection is between a trajectory of an object, the velocity and the acceleration, and then what that tells you about net forces, which in turn tell you something about what the free body diagram should look like. And we did this for this pole vaulter case. And initially we've looked at these three examples, one where the runner is sort of starting from standstill and has no velocity but is accelerating forward, one where the runner is moving at constant velocity, and then finally we talked about this more complicated case where the runner has just planted the pole vault in the ground and is starting to sort of push forward against that pole vault, that pole having the pole push back against them, and so on. So let's do one other example of that, and I'd like to focus on this example because it's one that actually probably takes the most thinking. This is the case where the runner is starting to be catapulted into the air. Their feet have left the ground at this point, and you can see that their velocity is sort of upwards and a little bit to the east, whereas the acceleration is upwards and a little bit to the west. So let's think about what that means for a free body diagram for this case. I'll attempt to first draw a cartoon that sort of captures the idea of that. So we have this pole vaulter here. And if you watch the videos, you'll see the pole vaulter is starting to swing their legs upwards at this point. They're still holding onto the pole at that point. And eventually they'll swing their legs upwards to invert themselves on the top of the pole. But at this point, they're maybe looking something like that. And we've figured out from looking at what we think the velocity is doing that the acceleration of the pole vaulter at this instant is up and to the left like that, which means that the net force must also be up and to the left. Okay, so how do we think about that from a free body diagram perspective? Well, let's cut this runner out of the rest of the universe. And you notice I'm cutting the runner out. I'm now not thinking about the pole as being part of the system. I'm rather just thinking about the runner as being part of the system. And let's think about what the forces are that are going to act on that runner. And so I will attempt to draw the runner. Let's give the runner two legs just for the sake of argument. All right, so what forces are acting? Well, we know that gravity is acting down, right? What other forces are acting? Well, there must be some force that is acting to the left in order to give me acceleration to the left. And I must also have some net force that's up. That is, I've got to offset gravity and also get some additional force up in order to give me acceleration up. And if I look at this, I've cut through interactions, and there are only actually two or three interactions I can cut through. One is the interaction between the runner and the Earth, right, the gravitational interaction. The other is the runner is holding onto this pole, right? And so if I sort of zoom in on the pole there, I've got the pole, and the runner's hand is on that pole. This is a hand, really. God. Oh, thank God I didn't go into art. But the hand is on the pole, and there are actually two possible forces that might be important. One is that there might be some normal force of the pole on the hand, right? The pole resists the atoms from the hand getting pushed into the pole, so there's a normal force. And also, to the extent the runner is gripping the pole, there could be a frictional force in one direction or the other. So if we think about this runner at this point, pretty clearly, first of all, there must be some normal force that's acting on the runner's hands. So I'll write N sub L and N sub R to denote the left hand and the right hand holding the pole. And furthermore, there probably is some sort of frictional force. And if you think about it, the runner presumably is holding onto this pole. The pole wants to push them backwards because the pole is bent, right? The pole would like to straighten out and push the runner backwards. So there's also some amount of frictional force that's acting on the runner's hands. Okay? And if I add all of these up, I'm pretty clearly going to get my gravitational force. I'll get some amount of friction. So this is mg. This is what my total frictional force is. And then some amount of normal force, right? And so presumably n sub r and n sub l must be quite a bit bigger than the gravitational force in order to give me a net force that's up and to the left, just like the acceleration was. Okay? And you can sort of see when you look at it this way that it's pretty clear that the runner must actually be being accelerated up and to the left at this point in order to sort of make these forces work out. And it also says that these normal forces have to be pretty darn big, which says that in fact this runner had better have some pretty buff arms in order to make this all work.